Hi everyone, this is Ehsan. Welcome to my YouTube channel, Ehsan and Smek. In this series, I aim to teach you how to solve complex mechanical problem using numerical method, especially in a way that also help you develop a strong research skill. While there are many numerical methods out there, we'll begin with the finite difference method, a powerful and classic tool, especially in fluid and heat transfer and in some areas of solid mechanics. I will walk you through the math, the logic, and the coding primarily in MATLAB and Mathematica. More than that, I'll show you how to approach this problem like a researcher so you can apply them in your thesis or research paper. I welcome all of your comment, question, and suggestion. If you find this valuable, please like and subscribe and follow along. This is just the beginning of a deeper journey into mechanic and numerical solution. Before we delve in the topic, it is mentioned that I will try to use the most high site reference to make and present since I want to guide you to reach the high quality scientific report. Therefore, at the end, you can see the reference I used. Let's delve in the topic PDE. PDE describe many essential physical processes that occur in nature, such as how heat is spread, how fluid flow, or how wave moves through air or solid. To understand these processes, we need both physical intuition and mathematical knowledge. In this series of presentation, we focus on common type of PDE using solid mechanics, fluid mechanics, and heat transfer. We'll also look at a few examples to show these equations behave and why their solution matter. Later, we also talk about a complex of PDE or a system of PDE and how they are used in numerical method. Let's now define PDE. What a partial differential equation is. As you know, a PDE involves a derivative with respect to more than one independent variable. This is different from an ordinary differential equation or ODE, which depend on just one variable. On the screen, you can see the example of PDE. The first one, EQ1, is linear and first order because it only involves first derivative and the coefficient are not dependent on the function itself. The second one is nonlinear and second order due to the square second derivative and the product with the dependent variable. And the third is called quasi-linear PDE. It is second order and nonlinear, but it is still linear with respect to the highest order derivative. Let me explain how read the symbol. Phi x means differential of phi with respect to u with respect to x. Phi x is the second partial derivative with respect to x, and phi xy is the mixed partial derivative with respect to x and y. PDEs arise in three types of problem: equilibrium problem, eigenvalue problem, and marching or propagation problem. Mathematically, they are classified as elliptic PDE, parabolic PDE, and hyperbolic PDE. Terms will cover later in more detail. Equilibrium problem depend on every boundary point. For instance, Laplace equation in a square with a fixed boundary temperature gives you a steady heat distribution everywhere inside the domain. Eigenvalue problem at the twist that solution only exists for a special constant lambda And marching problem like unsteady heat conduction or wave propagation require a stepping forward in time from initial data. Let's now connect the mathematical type of PDE to real physical example and marching strategy. Elliptic PDE, like Laplace equation shown here, model steady state problem. This describe conditions that do not change with time. For example, how temperature distribute in a metal plate with fixed boundary. Next are parabolic PDEs such as 1D heat conduction. This model diffusive processes over time. You'll notice that the solution evolved from the initial condition and we march forward step by step in time. Lastly, hyperbolic PDE model wave propagation like vibration in a string or sound wave or in plate or in beam. Here, both the shape and the speed of wave travel matter. And again, we march in time, but with different behavior than the diffusive case. These examples set the stage for both analytical and numerical technique use you'll see in future presentation. In this slide, we present the analytical solution to a classic steady state heat conduction problem using separation of variable. The governing equation is a Laplace equation, and we're working on a unit square domain with fixed boundary temperature. We assume the solution is a product of function x and function of y, leading to convert PDE to ODE. Solving these two ODE with boundary condition yield sinusoidal and hyperbolic solution. Three of the boundary conditions are automatically satisfied by the solution structure. The remaining condition on the both edge and the remaining boundary condition on the bottom edge tx equal to 0 is used to calculate the coefficient an. The final solution is expressed as an infinite series of eigenfunctions, each scaled by these coefficients. This is shows the mathematical implementation of the analytical solution. The function txy computes the temperature distribution using the first n term of the infinite series. Typically, a finite number like 50 provide good accuracy. The plot 2D and 3D is then used to visualize the temperature over the unit square domain. As seen in the plot, the temperature decreases from bottom where it's fixed at T0 and approach to the type and side boundary as expected from the boundary condition. That brings us to the end of this introductory video. We've seen the PD or how, and we've seen what PDs are, how they are classified, and why they matter in mechanical engineering. In upcoming video, I'll take you step by step through actual coding, deeper mathematical technique, and research strategy that work in real academic and industrial context. The reference I've used include two core texts, computational number 1, computational fluid mechanics and heat transfer by Professor Anderson and co-worker. Number 2, computational fluid dynamic by Professor J.D. Anderson. These are high quality, high cited resources in the field. I encourage you to explore them alongside this video series. Thank you so much for your watching. Don't forget to subscribe and stay tuned. The story continues. We'll go deeper in solving and coding real PD problem together. Have a nice time. Bye bye.